Physical Hydrology Lecture 11 on surface water. Why is it important to study surface water? Too much surface water, flooding, can be a major problem in both mountainous and lowland areas, but also too little water, water shortage, may be a major problem. Too much stagnant surface water may cause infestations of water-related diseases such as malaria, dengue, yellow fever, or bilharzia. Too little water, in itself a problem, may cause the little water that is available to be of bad quality. Also, too little surface water in a downstream country, because water is captured upstream behind a dam and used for large irrigation schemes, may lead to political unrest and conflicts between neighboring countries. All mentioned problems have unwanted effects on economy and health, and therefore in-depth knowledge of the overall water system, atmospheric water, groundwater, soil water and surface water, is needed to manage our water resources in the best possible, sustainable and peaceful manner. The picture to the right shows upward seepage behind a dike for one of the major Dutch rivers during high water. The picture has been discussed in Lecture 3 of this series. In 1995, rivers in the Netherlands rose to unprecedented levels, and the polder Land van Maas en Waal was one of the evacuated polders. Fortunately, disaster did not strike. We're about to witness an animation in plan view of the flooding of the polder Land van Maas en Waal in February 1805. The animation is made with the Delft flooding system model developed by Dr. Annika Hesselink and Delft Hydraulics, which is now Deltares. The flooding was caused by a dike breach due to a high discharge peak in the Waal River of almost 6,000 cubic meters per second on February 13th, 5 o'clock in the morning. Both the clock in the upper right corner and the red vertical line in the hydrograph of the Waal River at the bottom will show the progress of time. The darker blue the color, the larger the water depth. The animation shows that the evacuation time after the dike breach for the westernmost deepest part of the polder is slightly more than 1 day. Let's revisit Bernoulli's law. This figure shows the all-familiar piezometer, where we know the total energy of the groundwater at the piezometer screen to be equal to elevation head plus pressure head. Because flow velocities in groundwater are slow, we could disregard the kinetic energy term half mv squared in Bernoulli's law, but surface water flow usually is rapid, and in establishing the energy of surface water, we cannot disregard this term. After dividing by volume, uppercase V, water density ρ, and the acceleration due to gravity g, we obtain this equation where all values are expressed in length units. The kinetic energy term half mv squared has become v squared divided by 2g. This term is called the velocity head, with lowercase v being the water velocity along a streamline in meter per second. This figure shows a pitot tube, an invention by Italian-born French hydraulic engineer Henri Pitot. The tube is held with its lower opening opposing the water flow. The water flow in this figure is from left to right. Held in this way, a pitot tube converts the kinetic energy of the surface water flow into a pressure head that is equal to the velocity head hv. By measuring the velocity head hv in the pitot tube, we can determine the water velocity along the streamline as shown here. For precise measurements using a pitot tube, the water velocity v must be larger than 0.2 meter per second, or the velocity head hv larger than 2 millimeter. The total energy H total at the inlet point of the pitot tube thus equals the elevation head Z plus the pressure head P divided by rho G plus the velocity head V squared divided by 2G. Surface water flow is in the direction of the lower total energy. We could also have obtained the relation between velocity head and the water velocity along a streamline by assuming that over very short distances of flow, frictional energy losses may be disregarded. This then allows us to write that the total energy at 1 equals the total energy at 2, which, by using Bernoulli's law for both locations, is written out here. Please acknowledge that disregarding frictional energy losses over short distances and then setting the total energy at location 1 equal to the total energy at location 2 is standard procedure in fluid mechanics. See, for instance, the worked out examples in my book of Torricelli's experiment, which is equivalent to an artificial lake with a lower opening in the dam, the propagation velocity of a surface wave, which also holds for a tsunami, and the Venturi effect, which is the subject of exercise 5.1.2, etc. For all these cases and other such cases in section 5.1 of my book, this procedure is followed. Let's apply the procedure to the pitot tube. The total energy at 1 equals the total energy at 2, as stated here. Z1 equals Z2, stated here. The pitot tube converts the kinetic energy of the surface water flow into a pressure head that is equal to the velocity head hv. Thus, the pressure head at 2, which is P2 divided by rho g, equals P1 divided by rho g plus hv, as stated here. The water velocity at 2 is 0. When we insert all this in this equation, this is what we get. For the water velocity at 1, v1, we may simply write v, the water velocity along a streamline, in meter per second. This then is the relation between the velocity head hv and the water velocity v along a streamline, which is the same as established earlier. To measure the water velocity, usually a combined pitot tube is used. This figure shows such a tube. The combined pitot tube has an opening towards the flow that measures the total energy or total head, and a vertical opening on both sides of the horizontal part of the tube that measures the water height. Subtracting the water height from the total head delivers the velocity head hv, and from this the water velocity can be determined as shown here. Let's study ripples in the water. Whenever you throw a stone into a natural stream, study the movement of the ripples at the water surface this causes. You may observe part of the ripples to move upstream from the point of contact with the water. The propagation velocity of the surface wave caused by the stone's impact on the water then is larger than the velocity v of the water. If not, the ripple could not move upstream. We call this type of water flow subcritical flow, in Dutch subkritische stroming of stromend water. You may, however, also observe the ripples to be totally swept downstream. The flow velocity of the water v then is larger than the propagation velocity of the surface wave Vw. We call this type of water flow supercritical flow. in Dutch superkritische stroming of schietend water. When the water flow velocity v and the propagation velocity of the surface wave Vw are equal, the water flow is called critical flow, in Dutch kritische stroming. In theory, we would then have to observe the upstream part of the ripple to remain stationary at its point of initiation. Box 5.4 in my book shows that by assuming that over very short distances of flow, frictional energy losses may be disregarded, the standard procedure in fluid mechanics, this relationship can be established for the propagation velocity of a surface wave, Vw, which is sometimes also called the surface wave celerity. Vw is in meter per second. G is the acceleration due to gravity in meter per square second, and h is the water height in meter. The ratio of the water velocity v and the surface wave propagation velocity Vw is called the Froude number, after British engineer and naval architect William Froude. Thus, for subcritical flow, v is smaller than Vw, the Froude number is smaller than 1. For critical flow, v equals Vw, the Froude number is 1, and for supercritical flow, v is larger than Vw, or the Froude number is larger than 1. This sheet shows a photo of the bottom of my kitchen sink when the water tap is turned on, showing the transition from supercritical radial to subcritical turbulent water flow in everyday life. The transition is accentuated by the water rim, which is called the hydraulic jump. At the hydraulic jump, the water flow is critical. The following part of this lecture will show us that we can make good use of critical water flow, because only then, as we will come to see, are the water height and total energy level of the water flow related in a unique manner. The equation shown here is Bernoulli's law for surface water, but presented in a slightly different way. He is the specific energy in meter. It is the total energy of the flowing water relative to the stream bottom in meter. Qw is the specific discharge in square meter per second. It is the discharge per unit channel width of the stream in square meter per second. H is the water height in meter. It is the elevation head plus pressure head. And the first term to the right of the equal sign is equal to the velocity head v squared divided by 2g. For a specific discharge Qw of 0.5 square meter per second, we can insert values for the water height h and find the corresponding values for the specific energy He. This delivers this graph, which is called a specific energy diagram, graph of the water height h versus the specific energy He, both in meter. In this case, for a specific discharge Qw of 0.5 square meter per second, as established from this equation. The equation and corresponding graph show that there are two alternate water heights, two possible positive water heights h, for each specific energy value of He. With the exception of the minimum specific energy value He, the leftmost position on the graph, that relates to only one water height. This figure is the same as the specific energy diagram we just discussed, but now with the water height h shown on the horizontal axis and the specific energy He on the vertical axis. The rate of change of the specific energy He with the water height h is dHe dH is equal to the slope of a tangent line touching this curve. At a local minimum, the tangent line touching the curve is horizontal, and the slope of the tangent line then equals 0. In mathematical notation, dHe dH is 0. Setting the derivative of this equation to 0 and then reordering delivers that the specific discharge QW equals h to the power 1.5 times the square root of g, and that V equals the square root of GH. Thus, when the specific energy HE is at a minimum, the flow velocity V equals the square root of GH, which we already know as the propagation velocity VW of a surface wave. Only at this minimum specific energy, which is the only position on the graph that relates to a single value of the water height h and not to alternate water heights h, we have critical flow, a transition flow between subcritical and supercritical flow, or vice versa. Only at the minimum value of HE does HE relate to one specific value of h, that is there a specific relation between the specific discharge QW and the water height h. The below two equations only hold for critical flow. Thus, when the specific discharge QW equals the critical specific discharge, and when the water height h equals the critical water height, and when the water velocity V equals the critical flow velocity. Therefore, from now on, we shall provide these variables for critical flow with a subscript C. But let's first deduce which part of the graph describes subcritical and which part supercritical flow. For this, let's return to the original specific energy diagram. In the upper part of the specific energy curve near the one-on-one line, the water heights h are relatively large and differences between the specific energy HE and water height h are small. Thus, the velocity head hv and water flow velocities v are relatively small, and the energy of the water is predominantly made up of elevation and pressure energy related to the water height h. Thus, for the upper part of the graph, we must have subcritical flow. In the lower part of the specific energy curve, near the horizontal h is 0 axis, water heights h are low, and differences between the specific energy HE and water height h are large. Thus, the velocity head hv and water flow velocities v are relatively large, and the energy of the water is predominantly made up of kinetic energy related to the flow velocity v. Thus, for the lower part of the graph, we must have supercritical flow. Water flow at the dip, as shown here for the Souloise River and the Dévluy in France, can be regarded as critical, changing from subcritical upstream to become supercritical in the rapid. As the water flow is critical at the dip, it is possible to make a rough estimate of the river discharge, uppercase Q, in cubic meter per second, as shown here. Estimate the critical water height hc in meter at the dip and then calculate the critical flow velocity as the square root of g times the water height hc, with g of course being the acceleration due to gravity that nears 10 meters per second squared. Then estimate the cross-sectional flow area perpendicular to the water flow at the dip, which is the width at the critical flow location WC in meter times the water height HC in meter. Multiply cross-sectional area and critical flow velocity, and you have an estimate of the river discharge Q in cubic meter per second. The equation shown here is an example of a so-called QH relation. Also note the hydraulic jump just downstream of the small waterfall or rapid in this photo, where the fast-moving water collides with slower-moving water downstream, is swept upward and falls back on itself like a crushing wave. At the hydraulic jump, kinetic energy is explosively converted into turbulence and potential energy as the water flow changes from supercritical to subcritical flow. Here we have the earlier derived equations again, now specifically written out for critical flow, is indicated by the subscripts C, and where the specific energy HE is minimal. Thus, these equations only hold for critical flow. QC is the critical specific discharge in square meter per second, HC is the critical water height in meter, HE minus is the minimal specific energy in meter. Inserting this equation in this equation delivers that the water height HC at the location where the water dips or where the water flow is critical equals 2/3 of the specific energy HE minus in meter. This is an important finding that we can make good use of when we want to obtain a better estimate of the discharge than with the just discussed rough estimation at the dip, or if we want to monitor the changes in discharge over time. In the figure to the right, the specific energy diagrams for two specific discharges are compared, with the curve for the higher specific discharge to the right. The points of minimum specific energy HE minus, where critical flow occurs for different specific discharges, are given by the broken line. The upper parts of the curves are for subcritical flow, and the lower parts of the curves are for supercritical flow, as explained earlier. Estimating the discharge by visual inspection of water flow at the dip of a rapid, as presented earlier, is a rather crude method, as it's difficult to accurately estimate the critical water height from a falling water surface. For an accurate estimate of the discharge, we would like to find a relation between the discharge, uppercase Q in cubic meter per second, and the water height H1 in meter slightly upstream of the rapid, where the water flow is still relatively slow and deep, and where the water height can be measured accurately. Using Bernoulli's law, the energy equation, and the earlier established relation that the critical water height Hc in meter equals 2/3 of the minimum specific energy He, we can deduce such a relation. Try to get the main idea of the coming story. For details, you need to study pages 218 and 219 of my book. The figure here shows a side view of water flowing over a natural step in a riverbed. Over a very short distance of flow upstream of the natural step, we assume the riverbed to be horizontal and frictional energy losses as small enough to be disregarded. Remember, as I told you before, disregarding frictional energy losses over short distances and then setting the total energy at location 1 equal to the total energy at location 2 is standard procedure in fluid mechanics. The total energy of the water, the specific energy, is given as the upper broken horizontal line. Also, because the water flow upstream of the natural step is relatively slow and deep, we may assume the flow there to be subcritical and V1 to be negligibly small, thus the velocity head at 1 to be 0. Also, the critical water height Hc equals 2/3 of the minimum specific energy He. The critical water height is the water height at location 2. H2 thus is 2/3 of the minimum specific energy at 2. The specific energy level at 2 is the same as the specific energy level at 1. Because the velocity head at 1 can be taken as 0, H2 is 2/3 of H1. Setting the specific energy at 1 equal to the specific energy at 2 gives as end result the relation of V2 with H1, which can also be written as a QH relation between the discharge uppercase Q in cubic meter per second and the water height H1 slightly upstream of the natural step in the riverbed. This equation is equally well applicable to flow over a dam and to flow over a rectangular weir, which is a man-made rectangular shaped fixed construction and the equation may be modified to estimate the discharge from water height readings slightly upstream of man-made fixed constructions in the riverbed, such as V-notch weirs and flumes. Here you see some setups in the field. To the left, a photo taken in Java, Indonesia, where the water height is continuously measured upstream from a small V-shaped structure. And to the right, a photo from the Jura in France with a similar setup, but now behind a small rapid. This figure shows a weir, in Dutch meetstuw, a man-made fixed construction to force water in a brook or river to overflow and the water flow to become critical. More specifically, this figure shows both the upstream and side view of a rectangular weir, a rectangular shape cut into a plate of aluminium or other material, which is placed perpendicular to the water stream, forcing the water to flow through the rectangular opening. The edge or surface over which the water flows to become critical is called the crest. The earlier derived QH relation between the discharge Q in cubic meter per second and the water height H1 slightly upstream of the natural step in the riverbed is equally applicable as QH relation for a rectangular weir and may be written for different weir widths WC as shown here, where H1 is the upstream water height in meter above the level of the crest of the weir, thus with the elevation of the crest of the weir taken as reference level, or Z is zero level. The value of C may be adjusted to account for frictional energy losses due to contractions in the area of flow and at the edges of the weir. This figure shows an upstream and side view of a V-notch weir, in Dutch een V-vormige meetstuw, a V-shape cut into a plate of aluminium or other material which is placed perpendicular to the water stream, forcing the water to flow through its notch opening. The cross-sectional flow area A in the weir perpendicular to the water flow can be derived from the critical water height above the level of the crest of the weir in meter and the tangent of the angle theta divided by 2. Using this cross-sectional flow area A, and from similar reasoning as for water flow over a natural step in the riverbed, the QH relation for a V-notch weir with different angles theta of the V-notch can be deduced as shown here, where H1 is the upstream water height in meter above the level of the crest of the weir, thus with the elevation of the crest of the weir taken as reference level, or Z is zero level. The value of C may, similar as with a rectangular weir, be adjusted to account for frictional energy losses due to contractions in the area of flow and at the edges of the weir. As a practical tip, always place a large boulder downstream of a V-notch weir to prevent the force of the falling water from undermining the built construction. The photos below show the process of building a V-notch weir in the Bruggebach in the Goodland of Luxembourg. And these photos show two other examples of V-notch weirs in the field. Monitoring discharges can be combined with sampling of the suspended sediment load in a stream, either by hand, as shown to the left, or by a construction whereby samples are automatically taken at different water heights and thus discharges, as shown to the right. These figures in plan view and side view show yet another man-made fixed construction that forces water flow in a brook or river to become critical, a flume. A flume differs from a weir in that critical flow is not attained by water flowing over a crest under the influence of gravity, but by water flowing through a constricted structure. The constricted section, the throat of the flume, is formed by raising the channel bottom or by contracting the sides of the channel, or by both. The throat creates a drop in water level or pressure head analogous to the Venturi effect. See exercise 5.1.2. This causes first supercritical flow and then a hydraulic jump when the water flow decelerates to subcritical flow. Several types of flume exist. The rectangular standing wave flume, illustrated here probably being the simplest type, as water height measurements H1 upstream of the throat may be directly related to the discharge by this QH relation. The factor C may incorporate the channel width, different flume widths, and/or other key variables. This photo shows a flume in the field. An advantage of a flume over a weir is that a flume largely cleans itself. The bed load of a stream consists of particles, sand and stones, that are moved along the stream bed by rolling, pushing and saltation. The suspended load of a stream consists of particles, clay and silt, that are carried in suspension above the stream bed. Especially bed load, but also part of the suspended load, may accumulate upstream of a weir below its crest. As an example, sandstone areas are characterized by high bedload transports, causing a large accumulation of material behind a weir in a short time. As this accumulation has an effect on the QH relation, the accumulated material has to be shoveled out periodically, which is hard work. Hardly any such action is needed for maintaining a flume in operation. However, a disadvantage of a flume over a weir may be its higher construction complexity. In this lecture we have quite intensively applied Bernoulli's law. Note that H in the theoretical QH relations just derived always carries an exponent of a multitude of a half, which of course has to do with the velocity head playing an important role in surface water flow. This observation clearly distinguishes surface water flow equations from groundwater and soil water flow equations, where the exponent of the hydraulic head in Darcy's law and the Darcy-Buckingham, Laplace and Richards equations is always a full figure, 1 or 2, and never a multitude of a half. Good luck with the exercises, study well.